where the equipment should be, what equipment should be there. So all those good things that happen in our lab, he has a significant hand on that. What you see on that table is a significant, all the future of the lab, the guys who are taking over and getting more good equipment. And occasionally we do some really good things with it too. And you're gonna get to see some of that. So Stuart actually is a PhD student now. But the plan was that he should already be sitting on the industry side of the table. There are three good reasons why he's one is I wanted him to stay, and that has to say something about my persuasion powers. Because the cost of opportunity of being a student instead of an industry is not small. The other reason is when he gave me a draft of his master's thesis, I was super impressed with it, and I suggested that that should be a PhD thesis. And you'll get to see some of that. And the third reason is, I'm not too sure he actually wants to leave the lab. Which I get to enjoy. So without saying a whole lot more, I want to turn it over to the one and only Stuart Guest. All right.
Well, thank you, Patricia, for the introduction. Yeah, I'd like to thank, I know both these guys aren't here, but Curtis Bell and Joel Pepend. They were the ones who invited me, and I'm kind of sad that they're not here to see me. I know that it's kind of a great privilege to be standing up in here, up in front of you guys, especially when I'm still the new guy. You guys have way more experience and probably a lot more cool stories and demonstrations to show. So I'll hopefully live up to it today. So my thesis, which I started in 2010, is focused on hard-facing using tubular wires. And I've come a long ways in certain things, and hopefully some of the results will show you. It'll be interesting. I've got a lot of videos in here, so if you, after this good meal, you don't fall asleep, I hope you don't. But so without further ado, I'll jump in. Like Patricio said, I grew up in Westlock. It was actually a small farm outside of Westlock. Then came here for my undergraduate. Luckily, lucked out going to Welding of Associates in 2009 as a summer intern and fell in love with welding. Came back the following semester, and Matt Yarmich was, who I'm sure we're mostly familiar with in this room, was teaching a welding course. And then after that, I was just hooked. And Patricio, luckily, took me underneath his wing, and I guess the rest could be history. Fingers crossed, I should be finishing my PhD this year, and its pretty much focus is depositing nickel tungsten carbide overlays with hotwire assist technology. So, a little bit what we're going to talk about today. The actual overlays themselves and the welding of them, it's very difficult. There's not very many off-the-shelf solutions for this particular alloy solution. And then also tubular consumables. They've recently been developed, and while there's not much understanding of them, we'll go into some of these subtleties associated with it, especially when it comes to welding. Wear and energy extraction is a huge deal in this province. Basically, any sort of digging or drilling, the hard sand particles wear out our equipment extremely fast. We quoted anywhere between 2 to 3 shifts to a couple thousand hours. So as soon as that happens, the equipment downtime leads to a large expense for the company. And they pretty much occur by 2 mechanisms: erosion or erosion-corrosion mechanisms. And we need to protect the equipment with some alloys. For oil sands, which is going to be the basis of the focus of this, is nickel tungsten carbide. And basically the fundamentals of the process just work by having very hard carbides, which the sand particle skips along the surface of and does not wear out our part. Now, I'm sure people have heard the chrome carbide overlays before. They're the bread and butter kind of in the province, but when it comes to critical components that are in extreme service conditions, nickel tungsten carbide overlays are the only choice, really. So with these overlays, we have a number of things we have to consider. End user specifications, which I will not really go into at all today. That all depends on everything. Matrix chemistry, which is something we can control. The carbide type, which affects things drastically. And also the welding process, which kind of sums everything up. If you can't weld it, you could have the best material system ever. So end user specs, this is just very brief. Don't quote me on any of these numbers. This is just kind of what the general industry says. Typically an overlay thickness of 2 to 10 millimeters is required. During the wear test, the common measure is the ASTM G65 dry sand rubber wheel test. And they do 2 tests. And they'll do the first set of rotations of the procedure A and wear away the nickel matrix. And the actual measure of the performance of the overlay is on the second scar. And this is said to be more representative of the in-service wear conditions. End users can also specify carbide type and size distribution in the overlay. Wear rates often vary between end users, and then often within the same mine site, wear rates can vary considerably, and there might be a need to have specific carbide size distributions depending on the location within the mine. One of the most important things with these overlays is actually having enough carbide in our deposit. Usually it's spec'd out as 65 weight percent of tungsten carbide, which roughly equates to about 50% by volume. So half is going to be tungsten carbide, half is going to be the nickel matrix. And this is really important, and we'll see why when we start looking at these tubular consumables. Another thing, and I'm going to borrow the analogy from Patricio, I don't know how he came up with it a couple years ago. Tungsten carbide is like a sugar cube in hot coffee. It's very sensitive to temperatures. During welding, they have a very large energy to dissolve. They will preferentially dissolve. And as soon as that happens, our wear performance decreases drastically. So this is a little bit brief background to kind of bring everybody up to speed, and then we'll talk about some of the recent advancements in the thinking of the nickel tungsten carbide material system. So there's 2 parts. There's the nickel matrix and there's the tungsten carbide. The nickel matrix is nickel based with some small additions of chrome, boron, and silicon. The chrome, boron, and silicon basically serve to harden the matrix, get the hardness up of the overlay system. And typically you can purchase them based on bulk hardness of the overlay. And we'll discuss a little bit later, actually, one of the guys sitting in the room right here, Phil and Leonage, will discuss some of his results from his master's thesis he finished in 2009? 2010? There we go. Is that something to discuss? No, no, no. So when we look at these overlays, we can see our primary gamma nickel dendrites. Those are the first form. And then in the inside we have, in the interdendritic regions, we'll have a nickel and nickel 3 boride or nickel 3 silicide hard phase. And that's what gives our matrix our hardness. Now, carbide types are very important. There's a number of different types that you can buy when you go to do these overlays. And knowing which one you're going to start with plays a big role on what happens during welding and after welding. These are probably the 2 most common that you'll find used in these overlays in the province. First one, monocrystalline or macrocrystalline WC. It has a relatively high hardness, much harder than chrome carbides, for example. And the good thing about them is they're more resistant to dissolving. They will resist dissolving in the hot weld pool, so we'll actually keep our properties. On the flip side of things, we have these eutectoate W2C WC carbides. They're a little bit harder. The problem with the W2C phase, and that can be seen as this lighter phase right here, is it's very prone to dissolution. So you'll often see either kind of like this shark fin dissolving pattern here where the W2C is preferentially eaten away, or we'll see kind of these kind of halos or dissolution bands around these carbides. And that's evident of overheating or an incorrect weld procedure. And this will give us poor wear results, especially in an erosion-corrosion scenario when there's a wet fluid and there's corrosion issues. Recently, this was just patented in 2008, I believe. They actually managed to carburize the outside of these eutectoid particles. So they'll survive welding, and then you'll still have the good, hard nugget of eutectoid carbide on the inside. And recently getting a foothold in the province is this WC1-X because of lasers. It's a metastable type of carbide, meaning it really dissolves really fast at high temperatures, so it cannot be used successfully all that much in arc welding applications. You need the very rapid quench rates of laser welding. So companies like Apollo Laser Cladding do use carbides like this. So what happens with these overlays when we test them? And now this is getting into some of Philin's results here. I'm sure he recognizes this graph. And basically, he did a giant parametric study of every type of nickel alloy. And he did two things. He did it without carbide and then with carbide and looked at the effects. And it was something extremely interesting that nobody had seen ever before. These alloys, which performed good in the G65 test, just for reference, a lower mass loss indicates increased wear resistance. It lasts longer in service. And he found that certain matrices without tungsten carbide performed better than others. These were found to contain high amounts of chromium in them, and it managed to form a lot of very complex hard carbides and borides in the nickel matrix. And this followed conventional relationships. The harder we make things, the more wear resistant it's going to get. But something interesting happened. When they added tungsten carbide to the system, the roles were completely reversed. The alloys that were very hard and had a lot of chromium in them now performed the worst. And why was that? Well, they found that the chromium was extremely carbon hungry. As during the welding operations, it would preferentially suck away carbon from the tungsten carbides themselves. And that would give it these kind of secondary phases here that contain chromium, nickel, silicon, tungsten, and a host of other little special ingredients, which were extremely brittle. They really cracked very easy under loads. So now our periphery of our carbide would be susceptible to the wear of the oil sands. In addition to dissolving the carbides and decreasing the fraction. So we started out with 50% with no chrome, and then as we added more chrome, our volume fraction of tungsten carbide went down. So now our wear performance also goes down. And this was something that nobody had, they maybe theorized, but nobody had conclusively done a good study of these overlays. So when you're discussing nickel tungsten carbide overlays, there's a couple things you need to consider. Matrix chemistry. Does it have chrome? How is that going to affect your material system? What type of carbides is it? Is it eutectoid? So is it going to dissolve really fast if you have incorrect welding procedure? Or is it monocrystalline? What's the welding process? Is it plasma transferred arc welding? Is it laser? Or is it GMAW, MIG, which I'll be talking about in more detail coming up. Also, how was the carbide volume fraction measured? There's two kind of ways to do it. There's a regional analysis, so a high magnification microscope image of a small region of the weld, or there's an overall measurement. Now, the overall measurement is going to be more representative of the wear performance in service. And this is where, actually, Matt Dewar, he's sitting right here today. We told him about the problem, and over the weekend he got into it and built a computer program for us to measure these carbides. And basically, we can take an overall image, a very high magnification, high resolution image. Typically, some of these pictures are thousands and thousands of pixels big, so we have really good data to work from, and we can do image analysis on it. Now, measuring the tungsten carbide fraction in an overall weld bead is nothing new. What we're doing is now being able to separate out the primary tungsten carbides that survived welding and give us our good properties, from the detrimental secondary ones, which reprecipitate if we overheated our weld pool. And now we can differentiate between the two. And as it turns out, there's a drastic difference with the wear in the carbide volume fraction as we do this separation. So you can see here in A, we base all these funky colors don't mean anything. They're just random colors. They don't have to do anything with the size range. But as you can see, we've measured every little carbide. We've got our big primary ones that survive during welding. And then we've got all these little tiny angular ones, which are a result of overheating. They're reprecipitating. Now, if we do some operations on the image, now you can see we still have highlighted our primary ones, which are going to give us our good wear performance, and separated them from our detrimental little tiny reprecipitated ones, which do not improve our wear performance. And this is very important because the primary ones do give us our wear performance. As a result of all this image analysis, we can now quantify the carbide size and the distribution in the welded deposit. Basically, in this image, here we have our carbide size, and this is an arbitrary point, but we just said that any carbide smaller than 30 microns were reprecipitated. They would not help us in our wear performance in service. And this is something actually really important. Syncrude is kind of really looking forward to taking a look at this software that we've developed and taking it, using their extensive database of samples and maximizing the wear performance in service by looking at the carbide size distributions. Now we're going to switch gears a little bit and we're going to talk about welding processes. PTA right now is the current method of choice for depositing these overlays. Basically, it's a TIG torch on steroids for those of you guys who aren't familiar with it, and it uses a powder consumable. So here's a high-speed video we shot with our PTA machine in our lab. And here we can see our powders blowing in the rear of the arc. So the powders aren't experiencing the full heat of the arc and the weld, and they can survive welding. They can produce very high fraction overlays at moderate deposition rates and thicknesses. And this is really important, and it works very well. It's been very well quantified in the province for a number of years. Recently, laser cladding has been getting its foot in the door in the province, especially for small parts and intricate parts where fusion and penetration can be an issue on some of these, say, downhole drilling tools. Still uses a powder consumable, so within the powder is our nickel matrix and our tungsten carbides. And a characteristic of it, it's very high fraction overlays, but it is also very costly. It's a lot of capital expense for a company to get in the game and start producing these, especially since there's very few people that actually have direct experience with a laser system. And that leads us to pretty much the focus of my thesis, is using tubular wires. It's a very cheap alternative. Anybody with a standard MIG power supply can use tubular wires in the province, making it very attractive since the capital cost is small fractions of PTA and laser systems. Some of the things that we're learning is there's definitely no off-the-shelf solution for these tubular wires. We're in the process of developing this technology more. EATF is focusing heavily on these tubular wires as well and trying to make them work for the province. So smaller companies can do field repairs off the back of a truck to fix up a digger tooth, or they can use smaller capital cost equipment to do these high value added overlays while having good quality. And one thing we know that we've learned is the shielding gas and the power supply and the consumable are all linked. You cannot use a wire spool A from company A with shielding gas B. You need to have everything working together as a system to have good quality overlays. So one of the things that I'm going to focus on a little bit more is the tubular wires themselves. Now, these wires are like chrome carbide wires. There's no AWS spec, so every manufacturer is different. Just because you buy a 1.6 millimeter wire from company A does not mean it's going to be the exact same thing from company B. Another misconception is that it's called flux core. Well, there's no slag. You don't chip slag off the end. Some people can call them metal core. Well, they're not actually metal core because ceramic carbide is not a metal. So we could call it ceramic core or hard core wires. The characteristic of these wires is the sheath is pure nickel. Pretty much 99.9% pure nickel. And then inside wires is our tungsten carbide and boron and silicon powders, which harden our matrix. Now, evident from these pictures here, and these are just a sample of the wires we are actually testing in our lab, we can see two things. The sheath thickness varies considerably between manufacturers. If you look at B and C here, manufacturer B has a considerably thicker sheath. And what that leads to is a smaller internal area. And that is the internal area that carries our carbide. So if we want to have the maximum amount of tungsten carbide in our deposit, we need to have a thin sheath, the biggest internal area. Secondly, is the carbide size distributions can vary drastically between manufacturers. So are they all the same? Definitely not. We've pried apart all these wires, measured them a couple different ways, and all arrived at the same conclusion, that it really depends on the manufacturer and what the volume fraction in the wires is. I mentioned before that end users typically need 45 or 50 volume % of tungsten carbide to have good wear performance. Well, if we look at this graph, there's only 2, maybe 3 manufacturers of wires that meet this requirement. Even before we weld it, even before we lose carbides during the welding operation. And this is a big deal. And one of the things we can do, draw conclusions from, is we notice consumables C, D, and G. Well, these were the same consumables that had a very thin sheath. So they had a big internal area. They were able to stuff more tungsten carbide in the wire. And within the consumable manufacturers, they all have their magic recipes of powders on the inside. Some are just plain Jane wires, just tungsten carbide and a couple weld pool cleaners and arc stabilizers, while some are highly alloyed. Silicon, aluminum, iron, nickel, titanium, special sauce ingredients in there. So these wires all weld extremely different from one another. And unfortunately, it's up to whoever's purchasing these wires and whoever's going to use these wires to figure out what they want and which manufacturer is going to give them the best results. Just because the salesman says, oh yeah, it's got 50% in it, we know for a fact that some of these manufacturers claim there's 50% in it. I disagree, but I'll have to say
That's weight percent.
Actually, it's interesting. Some of the manufacturers, they have 50% by volume on the internal. Then I think they neglect to tell you add in the nickel sheath on the outside. So small little details that make a big difference. So the question is, why do we not use 50% wires all the time, especially in MIG? It makes the most sense. We have a high fraction wire. Why don't we use it during welding? Well, the answer is, since that nickel sheath is so very tiny that the current densities during welding is extremely high. So we need very good control of the welding operation to get stable metal transfer. So this is the video we shot in our lab of I think this is wire C or D, one of the very thin sheath ones, in short circuit mode. And while we did get okay weld deposits, the weld bead is not ideal. As you can see, there's a lot of undercut at the weld toes. It's not good. And also, the process stability was very hard to achieve. especially considering our end game was to have the maximum tungsten carbide in the weld deposit. For this particular consumable, the stable metal transfer range for a good deposit was about 20 inch per minute wire feed speed, which is extremely small and not ideal. One thing to know about these is you need to have the best welder, not your best welder working on these, but the welder that listens the best. These wires weld ugly, they sound ugly, but that's the way they have to be done. If your welder, if there's welders in the room, I have nothing against you. I have nothing against you. But if they tweak the knobs to make it sound a little bit better, all the expensive tungsten carbide that you just bought is going to disappear. It's either going to get lost during transfer, which we'll discuss in a bit, or it'll dissolve because you turn the heat up too much. So the extreme current densities of these wires force us to use modified short circuit, custom built waveforms. Unfortunately, there's not any available for any of these manufacturers yet. It's just a small market, especially when the big manufacturers sell welding machines worldwide. Small market, and while it's a big deal to us in Alberta, it's only a fraction of a percent to their total overall sales. And so that's part of the things we need to develop here in the province is solutions that are custom tailored to the problems we have here. And that was one of the mandates why the CCWJ was formed in 2010. Shielding gases also play a big deal. And just in case, these are all welds done in our lab with our high-speed cameras. Shielding gas plays a big deal in carbide fraction and arc stability. Now, here's the caveat. This only applies to just this one consumable that we tested. If I were to go use a different consumable, the effect of argon or oxygen might be reversed, it might not. It is very hard to tell. So that's why you have to use wire A with shielding gas A. It makes a big difference. So on the left, we have our CO2 welds with our wire's kind of hard to see here, it's kind of the black, but here we've got our molten nickel droplet and arc extinguishment period, and we get to see some spatter, some bright things kind of flying off the side here. And we'll discuss what those mean here in a little bit. Basically, what we found, and specific to MIG overlays, gas metal arc, with these tubular wires, is that tungsten carbide is non-wetting. Now this was previously not, it was maybe theorized. We saw some carbides maybe on the plate afterwards, but we didn't know the degree of the problem. And while using our high-speed videos, we found this to be an actual big problem. So this is lobular free flight transfer here. We get to see our tungsten carbides falling out and bouncing off the molten nickel weld pool like tennis balls. So we paid all this money for our wire, and then it just goes bouncing off the weld pool, ends up on our plate, and we have nothing. We've basically got a nickel overlay. We also observed the same problem in short circuit welds. My computer seems to be having a small hernia right now, but during the short circuit operations, in specific to the droplet formation periods, tungsten carbide falls out and sits on the surface of the weld pool. Now, as soon as the arc extinguishes and the current starts ramping up to reestablish the arc, basically it blows any of those carbides sitting on the surface clean off. And that's caused us to kind of remake a diagram in a very global sense that as soon as we go to higher productivity ranges, globular spray, there is no real true spray with these wires. We have increased dissolution. Basically, it's too hot, the carbides dissolve. And secondly, they bounce off the weld pool. So we end up with very terrible weld deposits. In short circuit, if we manage our heat inputs correctly, we're only dealing with this non-wetting mechanism. And this can be controlled through stabilizing the metal transfer with the correct welding parameters and the correct shielding gases. So this is a weld with oxygen, so it has the best arc stability. Again, caveat for this wire we studied here. And what we found is there's an ideal setting, and there's an ideal welding parameter that maximizes the amount of tungsten carbide that ends up in our weld deposit. And one thing to note is the manufacturer of this particular consumable spec'd out anywhere between 140 and 180 inch per minute as their recommended welding parameters. Well, what we found is actually dropping it down gives us better results. We get to maintain more carbide in the weld pool. And this consumable, we started with 35 volume percent in this particular consumable. It has more stable transfer because it has a thicker sheath than the thin sheath cousins. And what we get to see is after welding, we have about 29% in our weld. Or we're losing 20%. 1/5 of the carbide we just bought at $1,000 a spool or whatever they are has now been lost. It didn't end up in our weld, and that's a big deal. Now, people might say that, well, it's not very productive. Well, these wires, since they are tungsten carbide, are actually fairly heavy. So at this slow wire feed speed, 120 inch per minute, which is really slow, we are still depositing 7 pounds an hour with a 16th inch wire. So it's still relatively productive already at the optimum parameters. Now, if we're to use a bigger wire, say a 2 millimeter or a 2.4 millimeter, and we can find these optimum regions, our productivity goes up naturally. And so what we should be aiming for with these overlays is not to maximize productivity, but to maximize tungsten carbide fraction. That's really what the end users are buying. Not that you can put 20 pounds down an hour. They're buying, do you have 50% in your deposit? If not, next supplier. Second thing is heat input control. Now, again, this is for the consumable studied here. This may be different for other wires, but common measure of the quality of these overlays is heat input. Common thing is more heat input, less carbide. Well, that's true. Especially when we go to higher productivity, we go globular transfer, higher arc currents and voltages, we do dissolve our carbides. But within the short circuit region, we have something interesting happening. Within this region, we can have similar heat inputs, but at different wire feed speeds and travel speeds. So what this means, and based on the high-speed video and some fast Fourier transforms that we did on the voltage signals of the metal transfer, is the arc stability was vastly improved at this 80 inch per minute wire feed speed than the 165. So now we need to kind of forget about heat input a little bit. As long as it's low enough, we should be fine and not dissolve our tungsten carbides. We should look at maximizing our arc stability to make sure that all those carbides end up in the weld pool and don't get blown off when we establish our arc again. One of the ways we can do this is with something called hotwire technology. And this has been the main focus of my thesis, my source of hair loss for the last 3 years. But basically in GMAW alone, we're limited based on arc stability. Firstly, we have to use a thicker sheath consumable, so we actually have some operating parameter window. And then also, we do lose about 20–25% or more during the welding operation. And that's very limiting. So, hotwire technology, if you aren't familiar with it, is basically involves passing high currents and low voltages through a wire to heat it up. Very similar to a tungsten or incandescent light bulb. Pass some current through it, it heats up. So this is actually a steel wire here that I just heated up in our lab. And if you control your parameters right, you can control the current between the contact tip and the plate here such that you heat the steel up, this is a steel wire, to the solidest temperature. Really, really hot. So that means, it's like an oxymoron. Hot wire welding, you can decrease your weld pool temperatures, your leading arc heat input, because your wire is already preheated. You don't need any excess energy to melt your wire. I alluded to it already, it uses joule I²R resistance heating, same as a light bulb. We use a low voltage so it doesn't overcome the cathode and anode fall voltages, so typically below 11–12 volts, anything over that, you could be forming an arc at the end of the wire, which we do not want. And then we also want to pass high currents through our consumables to melt the wires, to get them preheated enough such that our weld pool can be colder. So our specific power supply we have in our lab uses a pulsed output. There is some out there that are constant current. Ours just happens to be pulsed. So in this case, we're pulsing 200 amps and then back down to 0, 100 times a second. So I'm going to nerd and geek out on you here for a second. But what can we do to understand the hot wire? It's a relatively unknown technology in the province. If anybody knows of anybody doing hot wire in the province, I want to talk to you afterwards. But it's commonly used for depositing corrosion-resistant alloys, especially for offshore and valves and that type of thing. The Japanese right now are using it to weld sheet metal for automobiles. And they can actually weld with this process fast enough that the robots cannot move any faster. They've maxed out robots. They can weld so fast. But the thing is, we're not using a steel consumable anymore. We're using a tubular nickel tungsten carbide consumable. And that gives us a couple brain cramps. So what can we do to understand the hot wire heating itself, since that is what controls the melting phenomenon? Well, we can, and using some of the research of one of Patricio's previous students, we started looking at this problem and breaking it down. Basically, we characterize it as a heat flux. That is a summation or a function of joule heating and the total, what the consumable is made up of. And break it down further, it's just this ugly, it's not that ugly, it's kind of elegant, but approximation of these various enthalpies to successfully bring our wire from room temperature all the way to melting temperature in a very controlled fashion. Now, what's good with a model that hasn't been calibrated somewhat? So this was kind of a little bit of a brain cramp again that I did last summer. How can we start moving from the theory and going into the practical and linking them together? How can we make it work? We did a couple different things. One of the things was use our high-speed video camera to characterize where the melting was happening along the length of the wire. If we didn't have enough current, we could basically see the wire plunge right into a weld pool. If it had too much current, it would actually prematurely melt and neck off and then break contact with the weld pool. When we had things just right, we could characterize the distance between the wires and the electrodes. Now this is where it differed from what's previously been done. Previously, they've neglected the contribution of arc energy to the hot wire. They just said, oh, it doesn't exist. Well, the arc, depending on where you look at it, is hotter than the surface of the sun. Well, it's 3 or 4 millimeters, a quarter inch away from your wire. You can bet it's going to play a little bit of a role in that. So with this calibration, we were able to actually quantify how much energy is coming from the arc into a function. And actually, we had a good fit with the data. It actually turned out somewhat half decent. And the nice thing with this is we were able to relate all these scientific brain cramp parameters back to real-world input data. How far our electrode is away, or how far our hot wire is away from the arc. What type of angle did we put our wire in? How high arc current do we have? We were able to bring it back to real-world parameters that welders and shop people have control of. So now we can control the hot wire. So this was a hot wire TIG weld that I did with a tubular nickel tungsten carbide consumable. And basically we can see that when you get the parameters right, we can melt all the wire before it runs and hits the bottom of the plate. When it does hit the bottom of the plate, it can skip along the steel substrate and underneath our arc. Now we're taking our wire and putting it underneath the hot arc. Well, that's what we tried to avoid in the first place with hot wire. When we get it right, you can see that all this nickel sheath here, so this is a weld, and I managed to freeze the wire in, and I cut right down the middle. And we can see that this nickel sheath with the right current is fully melted even before it gets to the bottom of the plate. So this is good. That means we're giving enough heat so we can turn our lead arc current down so we don't have to melt our consumable. Now,
why is it shrinking?
I didn't have the wire quite perpendicular.
Okay.
It's a little hard. It's a little hard to cut tungsten carbide.
That's fine. Go.
Yeah, especially when you miss by about 0.5 millimeter with the tungsten carbide. It's a little difficult.
Pretty good eye.
Yeah. I thought you were going to ask me tough questions, Reg. So, we started in 2010, 2011. Our thinking was to use hot wire TIG. We thought it'd give us the most control over heat input to the weld pool and then also melting. Now, as you can see, we can get awesome looking welds. We got 50% carbide. What we didn't know about was that these, since they're tubular wire, there's air in the inside of them. So as we're melting our consumable, we're injecting air right into our weld pool. As those droplets escape, it can cause weld pool reverberations that spit out droplets that contaminate our electrode. So while this looks awesome, I can only tell you, depending on the consumable, you can only weld 6 to 12 inches before your arc stability is gone. You have to change out your electrode. So for research, it's fantastic. Ultimate control, very high fractions, everything looks good on paper. Industry cannot use it. That's where I said, well, why don't we just switch out the TIG for a MIG torch? Now we can use 2 consumables, have higher productivity, and who cares if we contaminate the MIG torch? It'll just end back up in the weld pool anyways. Everything's good. So with our MIG torch, since we want to have a stable metal transfer, we want to use a thicker wire. We want to use short circuit transfer so we don't have too high of heat, so we don't dissolve those tungsten carbides. And we want to use a shielding gas that will give us the best arc stability. In this case, it was an oxygen blend. For the hot wire, since we're not forming an arc, we want to have as much carbide so we can inject it straight into the weld pool. We want to use a thin wire with a high fraction. And then we have to balance our wire feed speed with the size of the weld pool. Obviously, if we have a small weld pool and we feed in too much hot wire, we got cold lap problems left, right, and center. So here's a high-speed video of the hot wire. You can kind of see the hot wire here. It's kind of glowing. It's actually surprisingly difficult to high-speed image a bright welding arc and a glowing metal rod, but we can do it. And basically, with the hot wire MIG process, we can take an overlay fraction, a standard MIG overlay with 28%. It's not bad considering our consumable only started with 35%. And with the hot wire, bring it up to 36%. Now, one interesting thing is when you do the mass balance between the 2 wires we were welding with, it predicted 36% that we'd end up with a weld deposit. With Matt's program, we can actually measure. We got 36%. Everything is lining up perfectly when we account for that 20% non-wetting losses. Characteristic of the hot wire MIG, and we were not expecting this, is the weld pool is actually cold enough that any of that nickel sheath that did not fully melt ends up in the weld pool, and that's how fast our weld pool quenches. It's very cold. So here we got a piece of unmelted nickel sheath. If you don't believe me, I did the EDX on it. It is the nickel sheath. It's pure nickel. And we see that around the tungsten carbides, we don't have any dissolution evident that we can see. And I've measured a couple spots around here. There's nothing. So everything is looking good. It's also very repeatable. This is a G65 coupon, actually a double layer, and this is the corresponding cross-section to the same weld. We get to see a homogeneous carbide distribution. That means we're going to get relatively even wear performance across the entire overlay, which is good. For reference, this is about 6 or 7 millimeter thick deposit. So it is in, depending on the manufacturer spec, or the end user spec, within range what it wants. Now, the proof is always in the pudding. We did wear testing at Syncrude with Hugh Roth on their machine, and we see a drastic increase in wear performance compared to general MIG. Now, the 1 here indicates a single pass overlay, while the 2 is a double pass, so like a multi-layer, extra thick coating. What's interesting to note is our hot wire MIG overlay, this multi-pass one, is now competing, and this is I think some of the wear results from Phil's thesis, is now competing with a PTA overlay that has chrome in it. So, 5-10 years ago when PTA, there wasn't some of the new developments like Phil's doing, we're now competing with the technology that 10 years ago was the best. And one of the things we want to keep doing is develop it further. Both us and AITF are going on this problem, and hopefully we can end up reaching the Holy Grail, which is this guy right down here. Interesting to note is that we are exceeding deposition rates of the current PTA process. PTA, anywhere between 8 to 10 pounds an hour. Well, the hot wire MIG in its initial development stages that we're at is already outperforming in terms of deposition rate. Now, I say 8 to 10 pounds an hour for PTA. I know there is guys in the province doing higher deposition rate. This is just the data I have, so if you're doing, I don't mean anything against you if you are doing higher deposition rates. This is just the data I got, so I'm running with it. So, in summary, for our material system, it's very important to know what the matrix chemistry is. It controls a lot of the tungsten carbide dissolution and the wear performance as a result of that. Obviously, if you have too high heat input, carbides dissolve. And the matrix, carbide, and process are all dependent on one another. You need to consider what process somebody's talking about and what matrix and what carbide before you start comparing notes. Now with the tubular wires, which is what everybody really cares about, can it work? Yes, we just said that we're proved that we're on the path to making it work. There's a couple things we need to worry about and solve though. That non-wetting problem, that 20% loss of tungsten carbide. We need to work on getting that decreased so we can actually get all of our carbide that we paid for and want in our deposit in there. We need to focus on arc stability through custom waveforms, modified short circuits, that kind of thing, to improve metal transfer. And then the hot wire process has the potential to take all those non-wetting and arc stability things and then feed in more carbide to it. So now we can start getting higher deposition rates and higher quality. So with that, any questions? I'll accept easy ones. I figured there's going to be a couple for me.
That chart you showed that had all the elements for the different consumables.
Yeah.
And some of them had these weird ones that were put in. Did you find any of them welded better? Did you find any specific elements in certain wires help to weld better?
I haven't done sufficient welds to be 100% accurate on your answer. Yeah, this chart. It all depends on the shielding gas too, and the relative amounts. Like when we have sodium, fluorine, potassium, if one wire has more sodium and fluorine, it's going to stabilize the arc more than another one. So it's relative amounts, and those definitely the consumable manufacturers don't tell you. This table is constructed from me doing measurements on every powder. So I don't know the exact amount of magic pixie dust that they put in there. That would affect your answer, or my answer to you. But there is a difference, yes. How much? I don't know. Tanya?
Sorry, I'll keep going.
It's going to be the AITF.
Oh, that's good. I'll ask you about that. You're talking about shielding gas and how important that is. And yes, it is. But you're comparing between a 2% argon and a 30% CO2. So
Yes.
30% CO2 is going to have a lot higher potential than the O2. So obviously you're going to be dissolving much more carbides. So I don't even, is that a fair comparison? Saying
we
doing
look
a 5O2 to a 2O2 to an argon to a 2CO2 to a 5CO2 as a better comparison of arc stability rather than a high potential.
we have done what you just said, and we have looked in, and it doesn't matter. Our heat inputs here were still really low, and yes, the potential is going to vary. There was no evident carbide dissolution, no matter 30 CO2 or 2 oxygen. We didn't see any problems with it. Again, that's with this consumable only, right? And the main thing we found was just the stability of the transfer affected it. I probably forgot part of your question, didn't I? Maybe.
Stuart, you might want to mention about when they put some oxygen getters in the powders.
Yeah. It's plugged in, I promise. How about now? You live? For now. Okay, we'll go quick. Yeah, depending on what they put in, I can't tell you the manufacturer, but they do put in some oxygen getters. So when we put in a little bit of oxygen to the shielding gas, it was one cranky welding operation. There was flames and spitting and spattering. And it was wild, let me tell you. It sounded like a hissing dragon, actually. But yeah, so it really depends between the manufacturers, what they put in and how it's going to weld.
What kind of oxygen getters we have?
The one we looked at was graphite. So it reacted fairly strongly to oxygen.
So all the chemical analysis that you have on that table, that was from your group getting that as opposed to being supplied by the manufacturers of the wire?
Right.
Okay, that's
Yeah.
par for the course.
I do have the sheets from the manufacturers, and a lot of the stuff that I measured,
Yeah.
they don't mention. Or they just put it in the other category.
Yes.
Was there one? Yeah.
For the repeatability, are you finding a lot of variation between like different sections of the spool of wire or even different spools, or have you gotten to that point yet?
I haven't really got to it, but it seems to be consistent so far. Now, I know for a fact it does vary on the manufacturer. Some manufacturers is really consistent, others not so much. It's kind of like flux core from the 60s. Lovely stuff.
In the same vein of question, what about the same manufacturer supplying spools of wire? Is there
We
high
haven't went through
variability?
enough spools yet, and mainly because they're super expensive and they get donated to us.
Okay.
So we don't want to be too greedy and ask for.
So what happens when you run out and you can't do any more experience?
Hopefully they keep making them.
That's for future Stuart.
That's yeah, future guy. Yeah, with more hair and better looks. I don't know. Have you guys went through enough spools to tell? Do you have a comment, or you can't comment?
Yeah, they are different.
Okay. Yeah. We are working with a manufacturer right now, and they're always doing special tweaks. So it can vary considerably, yes, even though you're buying the same label of a wire. Yeah. Because these wires are still in development stages for most manufacturers.
Standardization.
Right. There's no AWS spec. There's nothing. You buy it on OD and cross your fingers and trust the salesman, which is unfortunate for everybody buying, because these things are, what is it a pound? I've heard a range, but I don't know if it's, I don't know if I get the most accurate information.
Yeah, you're looking like $2,000, $3,000 for a 30.
Yeah, so a full spool is a couple grand. So you gotta really trust the salesman. Yep.
Are you using any green steel?
No, we are not. Not on these. It hasn't been a need. We haven't started looking into the effect of it on the stress relief cross-checking. Right now, we're just worried about, can we get carbide in there?
What size is the samples you're using? Are they big plates or are they just little?
Typically, we'll just do stringer beads on a fairly large plate to remove any of the effects of the heat conducting and then rebounding off the plate walls.
Oh, okay.
Yeah.
What kind of a dissolution do you typically have?
Dissolution or dilution?
Well, that's what we call it.
Dissolution?
Substrate melting into your pool.
Okay, dilution. Okay. A little different. Well, as you can see here, here's our edge of the plate. I actually haven't measured it in terms of the standardized percentages, but it can be significant depending on the shielding gas. Or I don't know if I've got, this might take me a while to put through. But depending on the shielding gas and your welding parameters, you can minimize that considerably.
But did you ever measure iron content in that? FE from substrate?
Sorry, what was it?
EDS, I mean the weld pool.
Yes, I have done EDS and EPMA as well, and yeah, there is iron dissolving in, but it appears that the iron is not playing a role in dissolution. Our weld pool cools fast enough, generally, that if it was going to do something bad, it's not happening yet.
With the micro you showed, the hotwire thing, it looked like you had transverse cracking run through it.
It did,
Something
no.
distinct to the process. And how
Or
much
just
that
where I cut it.
works.
Yeah, I think next one, after this one right here?
Yeah.
Yeah. But I've only done a couple of these wells because this used, actually the one manufacturer of our wire discontinued the line, so going along your line. Unfortunately, it was one of our better ones, and they gave up on it. So, but yes, there is transverse cracking in it.
They're all stringer beads?
What's that?
They're all stringer beads?
No, they're transverse to the welding.
No, I know, but
They're
when you do those, are the stringer beads
Yes.
or oscillator?
No.
So is that something you see with a normal classic MIG weld, or is it particular to a hot wire?
I haven't done enough multi-pass standard MIG. I have seen this with a multi-pass MIG, depending on the welding parameters. I have seen actually worse cracking than this with a MIG, and it actually kind of goes down and just goes sideways, and that any sort of impact is just going to fall right off, right? But I haven't looked at enough of them to give you a conclusive yes or no. Yeah, partially because these wires are super expensive, and we get the tester packs because we don't pay for them. So I get used to it. Yeah.
What does it cost, I guess, per pound of the wire or whatever?
Well, it's about $2,000 for 30 pounds.
30 pounds.
So that's what, $60, $70 a pound.
Go up to 3,000.
Yeah. So they're not cheap. Definitely not cheap. But the overlays themselves are expensive. So, yeah, Caleb?
Do you have any idea how it actually performs?
We haven't done in-service components.
So
basically, all we've done is the G65 coupons.
right. Okay. So you're basing it off of, I guess, just metal off of it, right?
Yes. Yeah. Yeah. Yep.
Is it all, are all the wires that you're working for, are they basically off the shelf right now, or you had indicated that you are working with somebody, so to speak?
They're off shelf.
Off the shelf?
Except for the one that no longer is on the shelf.
Well,
But yes, they are off the shelf.
Yeah.
The problem is manufacturers are constantly updating them
No,
and slipping them into the lines, right?
Understood. Is anybody, and so you're going to the marketplace and evaluating what's out there, or is anybody bringing them out into you, so to speak?
Bit of both.
Okay.
Yeah, bit of both. You usually will try and get people to donate a spool to us.
Yeah.
And kind of with no holds barred, we'll do it. And we just won't tell people that that's your wire.
Right.
That's why I labeled them
Okay.
nondescript.
But I meant, and understood, I meant more so in a case of, if they're giving feedback, you know, each individual respective organization with respect to their products, so on and so forth, do you get any sense from them that the work that you're doing and the work that's being done here is of value enough to them?
Depends on the manufacturer, but yes.
Okay,
They do
yeah.
like working with us, and they do like working with AITF as well, because it
Sure.
helps them. We do free research for them, and it's all a good symbiotic relationship that benefits both parties.
Right, but you won't end up in a drug trial type situation. That's, you understand what I'm saying?
Yeah.
You don't want the research buried for somebody that it doesn't work out for, as opposed to somebody that it does work out for, so to speak. And that was why the question in terms of, you know, to what extent if someone puts a pill out in the marketplace, it is what it is, so to speak. If they're working with somebody with a medical association or something of that nature, I just use the analogy so that no names come up here in this conversation. But you know, do you have that receptivity from the manufacturers in terms of, guess what, there's a value to this, not just in terms of your research, but an ultimate market value that may swing somebody to plow a little more effort, energy, and work into getting something that we can use here, based on your research.
Most of this research, actually, this is probably the first big public outing of it.
Okay.
So it's relatively been quiet around here just because we haven't been showing people that.
I appreciate that.
But so far, we're still friends with all the manufacturers. We haven't had any problems yet. So
I wanted to say something. So there is, number one, we're still friends of all these guys, right? There is a significant difference between this and medicine. And I'll tell you what the difference is. Before you sell medicine, you believe you know everything about it, although they don't, right?
Yeah.
These things, no. This is super experimental, and the consequences are very different, right? If you wear a tooth a little bit early, nobody dies. It's your job, right?
I just
So in this thing, they give this thing to us, and we discuss some of the, we're not doing IP for them or anything, but as we learn, we give feedback, and some of them are very keen into this, and if all goes right, we might design like the pulsing waveforms that go with the particular wires. All those things are yet to happen. But the truth is, this thing is like before, right after the Wright brothers, the planes had 2 wings, 3 wings, tail in the front, tail in the back, whatnot. This is what these wires are. They look the same.
Yes.
They're not.
No, I was simply interested insofar as, and I understand that from a manufacturing standpoint of view, you need to make a certain amount of wire in order to make, you know, business work, so
Yes.
et cetera, et cetera. And that's why, in terms of, you know, the level of interest, not just in the testing of their wires, but really in the end application that it is that we're trying to deal with. You know, I was just simply inquiring in terms of, are you getting traction in terms of, gee, guess what? There's a market not just here, but eventually, and we're looking at potentially something special for you, you know, for the end user and business in general, or is it at this stage it's very embryonic and just working with what it is that you've got?
Working with what it is. The tubular wires themselves are relatively young still.
Yes.
So we still got to get a lot more understanding out before things start getting more tailored, if you will.
Yes.
Okay. Any more? Yeah.
So you kind of mentioned, I guess, if your research goes amazing and you have a utopian solution, you can do this off the back of a truck.
No.
No.
The learning and understanding we have on the MIG process alone, no hot wire, yes. That is if the welder listens to you, nothing against welders again. And and you have your welding parameters and procedure dialed in. Now the hot wire MIG, because that hot wire, it has to be inserted at a relatively accurate position. Too far back, it hits the solidified weld bead. Too far ahead, it'll hit the wire, the lead wire. That would be looking at a mechanized system. So those can either be robotic or hard automation, you know, CNC type things. Welding ID pipes, for example, like the torch apparatus themselves is actually fairly compact and small. So you can do small ID bores and that kind of thing. So hopefully, you know, they complement each other. The learning we get with the MIG will help the guys in the field, and also the hot wire MIG guys to do their stuff in the shop environment. And I think you had another one, yeah.
Yes, the carbide counting program.
Yes.
How do you know that it's a reprecipitated carbide? Like, do you do chemical analysis on it, or do you just know that there is such a large distribution of size in there? When they're cooking it, they crunch down the carbide, so you do get dust in there, and that's just what that is.
Both. Unfortunately, right now, where we draw that line between reprecipitated and the primary, the good ones, is completely subjective. It's basically looking at our weld, looking at those little tiny ones that, you know, are either the fines from the manufacturer or reprecipitated, and basically looking at the scale bar, and if they're 20 microns, we draw the line at 20 microns, and anything smaller than that does not get counted.
Just I've never seen reprecipitated WC. It's always like a 661, or that's why I'm a little bit.
I'm just labeling them as reprecipitated WC. We haven't done even chemical analysis on them yet. Yeah. But right now, basically, they're so small, anyways, that they don't do anything anyway. So we might as well just not count them and focus
That's
on.
not really true. I'm sorry.
Because
you haven't shown a G65 watt surface yet. That's what I'm going to tell you whether the G65 is relevant in the field or not. I'm sorry.
You know what? If you come, there's a seminar on May 16th. CWA is putting on. It's weld overlays, and you can ask Steph Giovelli in person from Syncrude.
Well, something about these precipitates. There is something we have done. We know there is some amount of dissolution when the liquid when it goes solid. They do reprecipitate. And there are two things we see. Number one is that they reprecipitate as smaller and jagged. And the other thing is that when you measure the composition or complex carbides, instead of being the tungsten carbide that has good ductility, these ones have chrome in them, they might have boron too. They don't have, funny that in carbide we talk about ductility, but tungsten carbide has a lot more, a lot less fragility than the other ones. So in this software that we made in-house, the whole point was, can we discriminate the reprecipitated from the others? And we have some thoughts how to go about it. Shape is certainly a factor, size is a factor. Right now we have implemented a shape, a size criterion, right? And so when we say smaller than that is for precipitated, really what we're saying is this. From our experience, what we see is small and jagged, right? That is consistent with what we have seen as for precipitated. We look at that size and we say, that size below is for precipitated. I believe we're much more or less on the ball, right? Now, the next stage of our software, if all goes right, is to account for shape, whether it's elongated or angular or something. So now it's not anymore just that it's smaller than this, but it's smaller within some size and jagged, right? And I see Matt's kind of here, but right.
No, I'm not worried about whether it is reprecipitated or you got it from the actual feedstock. I'm not worried about that.
Yeah.
I'm worried about the role they do play in the weld resistance.
Well,
that's what I'm worried about it, which you're completely dismissing that, which is not really true.
Well, let me tell you what I think, but all these things, again, like, I have an opinion, but if you don't like it, I have another one too. my first one, and is this, when they precipitate and they come as complex carbides, right? Because our interpretation is they are brittle, right? And when they are, so the matrix, although it's hard, can be worn out more easily. And that's the way we interpret these results from Thielen, right? In which he had the harder matrix, but the lower were resistance, right? So that's essentially what we're trying to discriminate. And because this common wisdom that harder is better for wear resistance, we see this opposite in some cases, and we believe it relates to the chrome and to the precipitates. So that's why we think it's very important to discriminate both of those. Let's talk again next year, and let's see if I still stick to this. But I think that's more or less where things go.
And we have looked. I have looked at some of the G65 wear scars in the SCM, and a relatively small primary, in this case it was a eutectoid carbide, was right next to a roughly the same size reprecipitated WC, and the primary was providing wear resistant. The matrix was wearing away around it because it was not fracturing. However, right next to it, that reprecipitated guy was just smashed and broken all up. But that's only one small region of the entire big overlay, right?
No,
so you got to take out the grain of salt.
Our experience is, when we are not using the full potential of the tungsten carbide in any of the build overlays. Most of the time, the matrix is one away; they just get knocked out.
Because you don't have enough carbide fraction,
so
right?
most of the time, you really need to focus on the matrix and not the carbide.
Well, you need enough.
And this solution is good for us in our system. So it's completely opposite.
We can discuss later.
So actually, in the interest of Stuart's hair, we'll do this one here.